Hello, welcome to my channel. This is Priscilla, your peer leader, and this is gonna be representing me. Either way, I do apologize again for canceling workshop last minute last week, but thank you guys for being also understanding. Again, the homework for this module is going to be optional and it'll be for extra credit, so you don't have to do it, but I would still highly recommend it just so you can see if you actually understand the material, as it will be tested on both the last exam and also for the final in the ACS. And so I'm actually going to be putting this in 2 different parts of videos, as YouTube it takes a very long time to upload big files, so I'd rather just do multiple videos, just covering each and every topic. I think other than that, if you still have any questions after watching these videos, please message me or ask me in person. If I don't answer you, just please keep on bugging me, as sometimes I think I answer but I actually don't answer, so I do apologize ahead of time. But now let's just go already into module 12. So the very first section is actually called acidic and basic salts. So actually this was introduced to you in the previous modules, and actually I think also in the exam as well, and this one's just pretty much telling you, if you look on your workbook on page 263, that if you have, let's say, conjugates of a strong acid plus the conjugates of a strong base, remember like that pull of war that I was talking about, if you have 2 strong, very buff guys who are both equally strong, if they're doing tug of war, it's not going to go anywhere, so neutral. If you have conjugates of a strong acid plus a weak base, that means now you have a very weak person like me. I never go to the gym, so very weak versus a strong guy who always goes to the gym. Okay, either way, so that's going to make an acidic because he's definitely going to win. However, let's say it's a weak acid plus a strong base. I guess I took steroids, I don't know. Then I would win, because now it's going to be a basic. And so we actually were introduced to that. An example how you kind of saw it was, let's say you have KCl, remember just to add water. And remember that this will dissociate into either hydroxide or H+. And you can also just know which goes with which, also due to the charges. You want a neutral compound, so the plus is going to go with the minus, and so forth. So this is actually going to give you KOH plus HCl. And we know it from knowing our strong acids and bases. Please don't forget them. You're still going to need to use them. That this is going to be a neutral compound, which means the pH will be equal to 7. And so you're just going to be seeing a lot of different types of problems where you have to do this. One of the examples I'll be actually going over is on the next page, on page 264 in your workbook. So one of the practice exercises is baking soda. I mean, I mostly put it in the fridge, but people also use it for toothpaste. Raise your hand if you do. I'm just kidding, I can't even see you. Either way, so always first write out the formula. So write out H2O, and that Na is going to make NaOH plus H2CO3. And this is a strong base, but remember H2CO3 is a weak acid, because if it's not part of those 7 acids, I'm sorry, you're not strong. And so overall, this is going to be a basic solution, so that should mean that pH is going to be greater than 7. Or the next one is NaCl. If you add it with water, this is going to be NaOH plus HCl, so very similar to like this problem, it's going to be neutral with a pH equal to 7. So not too bad at all. So I'll be going over a problem, or what if we have weak acids and bases. So remember in the pH module, if you have weak acids or bases, you need Ka, Kb values. So just to go over a quick, it's a little bit still like a review. So this is the practice exercise on page 265 on the very bottom. And so this one is determine the pH. And so they're saying that there is a solution dissolving 3 moles of NH3 in enough water to make 2 liters of a solution. And they're saying that for NH3 that the Ka is 5.6 times 10 to the minus 10. So first thing, write the reaction. So this is being dissolved in enough waters to make 2 liters. So you are adding water. So when you do that, you do get NH4 plus OH minus. So remember, this is hydroxide, right? So with hydroxides, would you use Ka or Kb? The answer is Kb. But then you're like, wait, but they give us Ka. You still have to use those formulas. So please remember how to convert Ka to Kb. When I did it, I believe Ka is about 1.79 times 10 to the minus 5. So when you do that, you're going to just do the ice table. Yes, ice tables have not disappeared just yet. And remember, water is not included. So these would be 0. And you already know your concentration for NH3 because you know that there's 3 moles in a 2-liter solution. So over here, NH3 is going to be equal to 3 divided by 2, which is going to be 1.5. So 1.5, since it's a reactant, it's going to be minus, plus, plus. Then you can put this down. So because your Kb was actually to the power of -5, you can't take away that x, so it makes it much easier. So put in your expression equal to products over reagent. And by just using algebra, I got x is equal to 5.2 times 10 to the minus 3. However, do note that this x is not equal to H concentration, but OH concentration. So you do have to convert to H concentration. So remember, you can either find the POH, then the pH, or you can just do the H times OH concentration is equal to Kw, which is 10 to the minus 14. Whichever way floats your boat, do it. But either way, I got a pH of 11.7. So this is very similar to what we already done before. So that's why I'm like, not too bad at all. So now that we're done with acidic salts and bases, now we're going to actually be going on to Lewis acids and bases. So let me flip this page. I'll switch my color because maybe not everyone likes pink. So now we're going to be talking about Lewis acids / bases. Very sorry if my paper is going all the way. I'm like holding my phone in one hand and this one, so I'm getting a workout. So either way, so before we talked about Bronsted acids and bases. So you're like, what the heck? What's the difference? So let's just do a little review. A Bronsted acid is a H donor, while the bases were acceptors. Right? And most of the time we could see this easily by just looking at the overall reaction and seeing, oh wait, there was 2 H's before and now there's only 1. So it's an acid and so forth. However, with Lewis acids and bases, most of the time you do have to draw Lewis structures in order to know about what is happening, because a Lewis acid. So also another note, Bronsted deals with H, so with protons, right? However, Lewis acids and bases deal with electrons, okay? So it's not talking about protons anymore. It's not talking about electrons. So on page 267, you can read it. So a Lewis acid is anything that accepts an electron pair, and a Lewis base donates an electron pair. So a common example is going to be water plus CO2, right? And so when you react these together, they actually join together into one big compound. So this is how it's going to look like in the end. So over here, you're like, okay, so what happened? And so what happened over here is that oxygen has these 2 lone pairs, right? So what it did is that it actually donated one of its electron pairs in order to connect to CO2, and that's how you get this like little bridge. So as you can see, oxygen lost that electron pair in order to connect over here. And while both of these both had double bonds, these double bonds, one of them, they transfer their pair of electrons to have 3 over here. And so this donated to itself, so it really doesn't matter if you donate an iPad to you, did you really actually donate? So that's why over here, water would be your Lewis base, and this would be your Lewis acid. And do Lewis structures, you can see which is which. I will give another example. So for instance, if we have NH3 plus BF3. So remember, Lewis structures, let's draw this out. You should have something like this, because you remember with the octet rule, 2, 4, 6, 8 plus BF3. And these are also going to join together to create B. Let's see, let me draw this out real quick. There we go. So what had to happen? So if you notice over here, nitrogen lost that lone pair. It's no longer there because what happened was that this lone pair connected to the boron to make that little bridge. So since it donated that electron pair, this would be your Lewis base since it did donate, and this will make it the Lewis acid. So that's why, that's how you can kind of tell between the difference is through that. So if you ever have to come a problem where it's like which is which, I would just recommend Lewis structures. I mean, it kind of says it in the name, Lewis acid base, Lewis structures. So I think that's pretty much it. In the next video, I'll be going over solubility and the KSV constant, so hang on tight.